In this tutorial, I'm going to walk through an example of a two-dimensional projectile problem. So essentially a ball getting thrown up in the air, but not straight up. And so we can imagine, let's say, a baseball pitcher throwing a ball at, say, 40 meters per second, but throwing at an angle of, let's say, 30 degrees. So what's going to happen is this ball is going to travel some arc and land somewhere over here. Okay, and we might ask questions about how far will it travel, how high will it go, how long will it take, and so on. So how do we do this? Well, let's label a few things. First, I'm going to label the time from the beginning of where they're starting to halfway. So when they reach the top, I'm going to label that T1, which is what I've used before. It's the same amount of time to the end, so that's also T1, and I'll often combine these and make the entire time a time T2. In order to do this problem, all we need to do is we need to break it up into two separate problems. So this projectile problem is equivalent to two problems. One problem is a horizontal problem where the ball is traveling simply to the right, and the other problem is a vertical problem where the ball is being thrown going directly overhead. Okay. Now we go back to the original picture, and we break up the initial speed into the horizontal and vertical problems. So the components. The component in the x direction is simply the speed, 40 meters per second, times the cosine of the angle. The vertical part is simply the speed, or the hypotenuse in this case, right? 40 meters per second times the sine of 30 degrees. So when you figure out the horizontal component ends up being about 34 meters per second. The vertical component ends up being about 20 meters per second. So going back to our two problems, we have a horizontal problem with a ball being thrown just horizontally at 34 meters per second for some amount of time. And we have a vertical problem of a ball being thrown into the air at 20 meters per second. Right, and we just tackle each one of those as an independent problem. Okay, so let's start with the horizontal one. That one's a little easy because gravity doesn't even work in that direction. So this object will go at a constant speed out until it lands at T2, which we know is also twice T1. The position at any given time in the x direction, that's what I'm calling, is simply now the speed, which is constant, at 34 meters per second, times the time. And when we look at the range, if we find out what T2 is, we can plug in T2 here and get the range, essentially the full length of how far this object will travel horizontally. Okay, now let's go to the vertical problem. Vertical problem goes, we throw a ball up, and at the very top it turns around and comes back down. The speed time plot for this in the y direction starts out at 20 meters per second and looks like this. The slope is negative 10 meters per second rise over a run of 1 second. So that's the constant slope, by the Earth. the height traveled will be this area here. That will be the height, which is labeled up here. And that will be the height. And this point here on the time axis is t1. And there's an equivalent t2 over on the x-axis. Okay. Let's scroll down a little bit here. The position at any given time. Sorry, I will do the speed actually in the y direction. We'll do that from this line. Is -10. The slope, meters per second every second, times the time, plus the intercept, which is 20 meters per second. At t1, this is equal to 0. And that leads to a t1 of 20 meters per second all over 10 meters per second every second. The units work out as seconds, and this comes out to be 2 seconds. So t1 is 2 seconds, and that gives us that tells us how long it is to the top. We can then go back. Now that we know t1, we can go back to the horizontal problem and find that the range is simply 34 meters per second times twice t1, or 4 seconds. And this gives 136 meters. That's how far it went. We can get the height, again, going back to this speed time curve, and it's the area under the curve. So the height is equal to 1/2 the base, which is 2 seconds, times the height, 20 meters per second. The units work out to be meters, and we end up with 20 meters as the height. And so essentially all we've done is we've taken a two-dimensional problem and broken it up into two easier one-dimensional problems. A horizontal component where the speed is constant and gravity doesn't act, and a vertical component where constant gravity acts, and we end up with a linear speed time curve, and then we can calculate both the ranges and the heights and everything else.